Good morning, my awesome tribe. I hope you're all well and doing wonderfully on this Monday morning. So I wanted to do a video today on the mitochondria again, surprise, surprise. But this time I actually want to focus on the electron transport chain and how it functions and the role of one of the nanorotors in it called the ATP synthase, and how the process of all that metabolism in the mitochondria actually generates light signals that the cell uses to coordinate and control all the biochemical reactions that happen in the cell. So, if you remember from my other video, I talked about the electron train transport, which basically is a series of proteins that are embedded in the inner mitochondrial membrane. And then electrons come into that and they flow down that like a wire, almost like an electric current. Now, at the end of that wire is a very special complex called ATP synthase. Now, it's a very interesting protein complex, but it's basically like a tunnel, and it spins at a really, really high rate. So it's between 8,000 to 9,000 rotations a minute. So as a reference point, a jet engine, like in a plane, would spin at around 4,000 to 5,000 revolutions a minute. So you kind of can get a sense of reverence and awe for how amazing that is. So basically, as that rotor spins really, really fast, hydrogen ions are pumped through it, and in that process, as the spinning of the ATP synthase happens, it creates ATP, which is our energy molecule, and the process of electrons tunneling down, we also create metabolic water or intracellular water. So the oxygen is drawn in to the magnetic field of the ATP synthase, because as a moving charge spins, it creates a magnetic field. Oxygen, being paramagnetic, gets drawn to that, and then oxygen is what we call the terminal electron acceptor. So that creates this tension between the beginning of the electron transport chain and the end. Okay, so we have this high tension here. So when there's high oxygen tension, you have really lovely electric current flow. Now, I thought about this and thought, what could I use to explain this in a really cool, fun way? And then the idea came to me. Okay, do you remember these wind-up torches that you can get for camping and stuff, right? I mean, they're a pain in the ass because you've got to keep winding them to get them to work. But what I want to show you is this. If you imagine that this is a bit like the ATP synthase, right? So if I'm going to turn it on there, okay? As I spin this, you can see the lights getting stronger and stronger and stronger and stronger, right? Okay? The same thing happens in your mitochondria, okay? As the ATP synthase spins, okay, you have a stronger electric current coming down, and that then creates all these biophoton signals that you can get, that the mitochondria creates. So we know from lots of different research papers published that the mitochondria produce the bulk of the biophotons, or what they call ultra-weak photon emission from cells. So we know all living cells emit very low levels of light. And the really interesting thing is with biophotons, they've measured that they go all the way from 200 nanometers up to almost 950 nanometers. For those of you that are physics geeks like me, you know that's in the UV to the infrared range, okay? So the way I like to think about it is that your mitochondria produce this rainbow of colors. So I always think a healthy mitochondria is like having a lovely rainbow, okay? So you can see we go all the way from the red all the way to the purple, which is going into the UV. So a nice healthy mitochondria is going to have lots of color. Now, we can't see this color obviously because it's too weak to be noticed by picked up by the photoreceptors in our eye, but certain photomultipliers and devices can actually measure this. And so what they're finding now, and what they're starting to look at, is can we measure photon emission from cells to pick up certain disease processes earlier. So before it actually shows up in various biochemical cascades, can we pick up the change in light frequency first? Which of course comes from mitochondrial dysfunction. So isn't that super cool? All right, so basically, better ATP synthase. It's working again. Okay, better ATP synthase. Stronger electric current. better light from their mitochondria and better cellular signaling. Okay, and then lots of lovely light throughout your body. Okay, so I hope that helps. It makes it a little bit easier to understand. I will put up some diagrams of the mitochondria so you can get a bit of an idea. There's some fantastic people to follow on this as well. If you really want to deep dive into the biophysics of it, Dr. Jack Kruse is amazing. So he's a neurosurgeon overseas. You can find him on, I think it's jackkruse.com. Incredibly in-depth though in the physics. This is like a really light and easy overview of it. But that's amazing stuff that's coming out around the biophysics of cells and how they actually respond to and emit light and use light frequencies to modulate the hundreds of thousands of chemical reactions that happen every single second in your cell. Okay, so that's my talk for today. I hope that's of interest, and I hope that's kind of inspired you to think about spinning those little ATP synthases faster. Just an aside too, we also know that those chromophores in the mitochondria all respond to certain frequencies of light. Okay, so for example, when you shine red light on the mitochondria, so like in photobiomodulation, which is really big right now, like red laser therapy, red light therapy, it actually increases the spin of the ATP synthase, and it increases the function of the protein before it, which is called cytochrome C oxidase, which actually makes the intracellular water. So that cytochrome C oxidase actually has 4 red light chromophores in it. Okay, so that's like super exciting, and again, shows you that our bodies are not just responding to chemicals, but really at a deeper level, our body uses and signals with light. Okay, fabulous. Have a wonderful day, and I will talk again soon, I'm sure. For those of you that are interested, my live talk is coming up in March at Red Tree Theatre in Tuggerah. There is an online option if you want to have it streamed. I will be using lots of props like my wind-up torch, like my feather boas. I'm going to be explaining different hormones as different characters. I want it to be a lot of fun because I think health and science and cells are super fun and super interesting. I do a lot of theatre, so I want to make it entertaining for you so that you walk away feeling inspired and entertained and not walking away going, well, that was a boring health talk. Okay, so I would love to see you there, and if not there, please feel free to do the online streaming option, but I guarantee you won't walk away thinking that it was a boring talk. All right, cool. Okay, see you guys. Bye.